Hello everyone, welcome to EPG Pathshala. Thank you for having me here. My name is Dr. Saif Saeed. I am Assistant Professor in Jamia Millia Islamia. And I'm going to be speaking to you about the basic principles of remote sensing. This module is divided into 8 major headings that includes an introduction part followed by the definition and scope. We'll be moving on to the electromagnetic waves covering electromagnetic spectrum. Next section will be radiation terminology covering radiation laws and fundamentals of black body radiation. EMR interactions with the atmosphere will also be looked at, followed by atmospheric windows and interaction with the Earth's surface, and at the end, image resolutions will also be covered. At the end of this unit, student will be able to briefly explain energy sources, the components of the electromagnetic spectrum that collectively forms an integral part of remote sensing technology, concept of surface temperature and radiation laws and terminology, the essential theories that describes the characteristics of electromagnetic radiation, energy interactions in the atmosphere, scattering, absorption of energy in the atmosphere, atmospheric windows, electromagnetic radiation, interaction with the Earth's surface, and various reflectance characteristics of the Earth's cover types. Various types of resolutions that describes the utility of the spatial data forms for a variety of applications. So let's start with the general introduction about remote sensing. Humans are closely associated with remote sensing in day-to-day activities by collecting and inferring useful information about the surroundings sensed through our eyes. Our eyes act as sensors which are limited to record only the visible portion of the electromagnetic energy, and our brain act as a processing unit which stores the viewed information for a limited number of days. This limitation forced mankind to develop a technique capable of acquiring information about an object or phenomena covering almost entire range of electromagnetic spectrum. The data also acquired is stored in some medium, for example, CDs, hard disk, etc., for future interpretation and analysis. The remote sensing technology has advanced particularly towards variety of applications related to land, water, and atmospheric issues, for example, water resources, development and management, soil and mineral explorations, agriculture, land use practices, air quality monitoring, disaster management and mitigation, ocean studies, and many more. This module attempts to provide a reader a basic understanding of the concept, capabilities, and limitations of remote sensing technology. Moving on to the definition and scope of remote sensing. As discussed, our eyes are excellent example of a remote sensing device that are capable of gathering information about the surroundings by judging the amount and nature of the reflectance of visible light energy from some external source, such as the sun or any artificial source of light, as it reflects off objects in our field of view. In the broader sense, the term remote sensing can be defined as the science of acquiring information about the Earth using instruments which are not in direct contact with the Earth's surface or features, usually from aircraft or satellites. Instruments aboard satellite or aircraft is usually a sensor which is capable of acquiring information in the entire region of electromagnetic spectrum. Every remote sensing process involves an interaction of incident radiation falling over the target of interest, in a sense that the radiation incident over the target is altered on account of the physical properties of the target and reflect back the incident radiation which is recorded by the sensor. This is illustrated by the use of imaging systems where the following 7 elements of remote sensing are involved. Referring to figure 1, the 7 elements on the basis of which remote sensing technology works are as follows. Source of illumination, which is marked as 1 in the figure 1. The foremost requirement for any remote sensing process is to have an energy source which illuminates or provides electromagnetic energy to the target of interest. Radiation and the atmosphere, marked as 2 in figure number 1. As the energy propagates from its source to the target, it interacts with the atmosphere as it passes through. Interaction with the target, marked as 3 in figure number 1. Once the energy makes its way to the target through the atmosphere, it interacts with the target depending on the characteristics of both the target and the radiation. Recording of energy by the sensor, which is marked as 4 in figure number 1. After the energy has been scattered or emitted from the target, a sensor is required to collect and record the electromagnetic radiation. Transmission, reception, and processing, marked as 5 in figure 1. The energy recorded by the sensor is transmitted often in electronic form to a receiving and processing station where the data are processed into an image in the form of hard copy or digital. Interpretation and analysis, marked as 6 in figure number 1, is processed image is usually interpreted visually or digitally or electronically to extract information about the target which was illuminated. End users and application, marked as 7 in figure number 1. The last element of the remote sensing process is achieved when useful information is extracted from the imagery to reveal new information or assist in solving a particular problem. Some of the important applications of remote sensing technology include environmental monitoring and assessment, global warming, etc., land use, land cover, global change detection and monitoring, prediction of agricultural yield and crop health monitoring, sustainable resources exploration and management, ocean and wetland studies, weather forecasting, defense and military surveillance, broadcasting, telecommunication, etc. Next section is the electromagnetic radiation. Electromagnetic radiation, also called as electromagnetic energy, refers to all energy that moves with the velocity of light in the form of waves. The source of EMR is the subatomic vibration of photons and is measured in terms of wavelength, propagation of electromagnetic waves with the speed of light, which is illustrated in figure number 2. Sun is the main source of EMR or electromagnetic radiation that travels through space in the form of waves that are either reflected or absorbed by the objects, mainly on account of size of the wavelength, which is described by distance of successive wave peaks and is represented by Greek letter lambda. Wavelength is measured in meters or some fraction of meters such as nanometers, that is 10 to the power minus 9 meters, micrometers, which is again 10 to the power minus 6 meters, centimeters, that is 10 to the power minus 2 meters. Frequency refers to the number of cycles of wave passing at a fixed point per unit time and is normally measured in hertz. Wavelength and frequency are inversely related to each other. In other words, as one increases, the other decreases. This relationship is expressed by a relationship C is equal to lambda into nu, where C is the speed of light, which is 3 into 10 to the power 8 meter per second. Lambda is the wavelength in meters, centimeters, micrometers or nanometers, and nu is the frequency in hertz, which is cycles per second. It can be inferred from equation 1 that object releases energy above absolute zero temperature, which is referred to as the electromagnetic energy. Hot objects emit higher energy as compared to cold objects that emit less amount of energy. Now the above section follows the subheading, which is the electromagnetic spectrum. The electromagnetic spectrum covers the entire range of photon energies arranged in increasing order of the wavelengths on a logarithmic scale, which is again illustrated in figure number 3. The electromagnetic spectrum ranges from the shorter wavelength, including gamma rays and X-rays, to the longer wavelengths, including microwaves and radio waves. Almost the entire range of electromagnetic spectrum is useful for remote sensing in a way that every band provides a useful information about the object of interest. Sensors on board Earth resources satellites operate in visible, infrared, and microwave regions of the electromagnetic spectrum. Let us now discuss the spectrum regions in order of increasing wavelengths and decreasing frequency. Ultraviolet. The ultraviolet region of the electromagnetic spectrum lies just beyond the violet portion of the visible wavelengths. The ultraviolet region has short wavelengths, which ranges between 0.3 to 0.446 micrometer, and high frequency. Ultraviolet wavelengths are used in geologic and atmospheric science applications, where geologic applications includes mineral exploration. Next one is the visible light. This is the portion of electromagnetic spectrum to which our eyes are sensitive and perceived as colors. The visible light covers a very small portion of the spectrum ranging from approximately 0.4 to 0.7 micrometer, and due to this small wavelength range, the visible portion of the electromagnetic spectrum is plotted on a linear scale so that individual colors can be discretely depicted. Refer to figure number 4 for visible spectrum. The visible light comprises of discrete colors with red at the long wavelength and violet at the short wavelength end. The visible colors and their corresponding wavelengths can be summarized in micrometers as violet from 0.4 to 0.446 micrometers, the blue color which ranges from 0.446 to 0.5 micrometers, green color which ranges from 0.5 to 0.578 micrometers, yellow color which ranges from 0.578 to 0.592 micrometers, orange 0.592 to 0.620 micrometers, and finally the red color ranges from 0.62 to 0.7 micrometers. Infrared. The infrared region covers the wavelength range from approximately 0.7 micrometers to 100 micrometers, covering 100 times more space than the visible portion of the spectrum. The infrared region is generally divided into two categories based upon their radiation characteristics, that is, reflected infrared and emitted thermal infrared. The reflected infrared region is used for specific remote sensing applications similar to radiations in the visible portion. The reflected infrared covers wavelengths approximately from 0.7 micrometers to 3 micrometers and is mainly employed for monitoring the status of healthy and unhealthy vegetations, as well as distinguishing among vegetation types. The thermal infrared differs from visible and reflected infrared in a way that this energy is radiated or emitted from the Earth's surface or objects and characterizes in the form of heat. The thermal infrared covers the wavelengths from approximately 3 micrometers to 100 micrometers, as these wavelengths are used for monitoring the temperature variations of land, water, and ice. Microwave region. This portion of the spectrum is of recent interest to remote sensing and wavelength ranges approximately from 1 millimeters to 1 meter. The shorter wavelengths have properties similar to thermal infrared region, while the longer wavelengths are used for radio broadcasting purposes. Microwave remote sensing is used in the studies of related to meteorology, hydrology, oceans, geology, agriculture, forestry, and soil moisture sensing. Next topic is the radiation terminology. The concept of electromagnetic radiation involves various terminologies that forms the basis of many important radiation laws widely used in remote sensing based analysis and modeling. One of the important radiation term is the radiant energy, which is defined as the energy carried by electromagnetic radiation and is expressed in the unit of joules. Another term is the radiant flux, represented by Greek letter phi, which is the radiant energy transmitted in a radial direction per unit time and is expressed in watts. In other words, the rate at which the photons strike a surface is called as the radiant flux. Radiant intensity is the radiant flux radiated from a point source per unit solid angle in the radial direction and is expressed in units of watts per spectral radiance. Irradiance is the radiant flux incident upon the surface per unit area and is expressed as a unit of watts per meter square. Radiant emittance, also termed as radiant excitance, is the radiant flux radiated from the surface per unit area and expressed in a unit of watt per meter square. Radiance is the radiant intensity per unit projected area in the radial direction and is expressed in the unit of watt per spectral reflectance. Radiance is also described as radiation field dependent on the angle of view. Now let us discuss some of the important radiation laws. The electromagnetic energy follows certain physical laws as it moves away from the source. Planck ascertained that electromagnetic energy is absorbed and emitted in discrete units called photons. The size of each unit is directly proportional to the frequency of energy's radiation. Therefore, Planck's theory proposed that electromagnetic energy can be quantified by its wavelength and frequency, and its intensity is expressed by capital Q, which is measured in joules. Planck defined a constant h to relate frequency nu to radiant energy capital Q and is expressed as follows: Q equals to h times nu. Since as per equation number 1 discussed in the above section, therefore equation 2 can be rewritten as Q equals to h into nu upon lambda, where Q is the energy of photons in joules, h is the Planck's constant, which is 6.6 into 10 to the power minus 34 joules, c is the speed of light, which is 3 into 10 to the power 8 meters per second, lambda wavelength in meters, nu is the frequency, which is cycles per second or hertz. Now let us take a look at the fundamentals of blackbody radiation. All objects with temperature above absolute zero emit electromagnetic energy, whereas the amount of energy and the associated wavelength depend upon the temperature of the object. As the temperature of an object increases, the quantum of energy emitted also increases, and the corresponding wavelength of the maximum emission becomes shorter. The above hypothesis can be expressed by using the concept of blackbody. A blackbody is the hypothetical source of energy that behaves in an idealized manner such that it absorbs all or 100% of the radiation incident upon it and emits back or radiates the energy as a function of temperature. The Kirchhoff's law, Stefan-Boltzmann law, Wien's displacement laws explain the relationship between temperature, wavelength, frequency, and intensity of energy. Now let us look at the Kirchhoff's law. Kirchhoff's law states that the ratio of emitted radiation to the absorbed radiation flux is the same for all black bodies at the same temperature and forms the basis of the term emissivity, which is represented by a Greek symbol epsilon, which is defined as the ratio between the emittance of a given object, which is symbolized as capital M, and that of a black body at the same temperature, which is again symbolized as capital M suffix B, and the equation is written as emissivity or epsilon equals to capital M upon capital M suffix B. The emissivity of a true black body is 1 and that of a perfect radiator or a white body is 0. This implies that all objects have emissivities between these two extremes. Now the second law is the Stefan-Boltzmann's law. The Stefan-Boltzmann's law defines the relationship between the total emitted radiation, which is expressed in watts per centimeter square, and temperature capital T, which is measured in Kelvin. The relationship proposed by Stefan-Boltzmann is capital W equals to sigma into capital T or temperature to the power 4. The total radiation emitted from a black body is proportional to the fourth power of its absolute temperature. The constant sigma is the Stefan-Boltzmann constant, which is 5.6697 into 10 to the power minus 8 watts per meter square Kelvin to the power 4. In short, Stefan-Boltzmann's law states that hot black bodies emit more energy than cool black bodies. The third law is the Wien's displacement law. This law specifies the relationship between the wavelength of the emitted radiation and the temperature of the object, which is given by lambda equals to 2898 upon capital T, where lambda is the wavelength which the radiance is at a maximum and capital T is the absolute temperature in Kelvin. As objects become hotter, the wavelength of maximum emittance shifts to the shorter wavelengths. This law is useful for determining the optimum wavelength of the object having temperature T Kelvin. With the help of these laws, temperature, radiant energy can be determined from an object's emitted radiation. Now, moving on to the interaction of electromagnetic radiations with the atmosphere. The Earth's atmosphere is capable of transmitting the entire electromagnetic radiation used for a variety of remote sensing applications. However, the electromagnetic radiations get affected as these passes through different layers of the atmosphere. The quality of image captured through aircraft-borne sensor is less affected by the atmosphere as compared to the quality of image which is captured by satellite-borne sensor, which is severely affected due to the fact that radiations passes through the entire depth of the Earth's atmosphere. The electromagnetic energy passing through the Earth's atmospheric layers is subjected to alterations by two very important physical processes, namely scattering and absorption. Now let us take a look at scattering. Scattering of electromagnetic radiation takes place when gas molecules and particles present in the atmosphere interact with it and redirects it from its original path. Refer to figure number 6. The amount of scattering depends on several factors, including the wavelength of the radiation, the abundance and size of the particles or gases, and distance of the radiation travels through the atmosphere. Generally, there are three types of scattering which takes place through the Earth's atmosphere, namely Rayleigh scattering, Mie scattering, and non-selective scattering. Rayleigh scattering takes place when the suspended particles are very small, mainly comprising of oxygen molecules or dust particles, as compared to the wavelength of the radiation. This type of scattering causes shorter wavelengths of the energy to be scattered much more than the longer wavelengths, and therefore the law is governed by the principle of reciprocal of the fourth power of the wavelength and is expressed as Rayleigh scattering equals to the reciprocal of lambda to the power 4, where lambda is the wavelength in meters. This type of scattering is dominant in the upper layers of the atmosphere, where tiny dust particles and gas molecules largely predominates. Rayleigh scattering is responsible for the blue color of the sky, since blue color is scattered the most on account of the size of wavelength smaller than the size of dust particles and gas molecules. The second important type of scattering is the Mie scattering. This type of scattering occurs when the particles are just the same size as the wavelength of the radiation. Dust, pollen, smoke, and water vapor are the common causes of Mie scattering, wherein the longer wavelengths are scattered the most. Mie scattering is more dominant in the lower atmosphere layers within a range of 0 to 8 kilometers. Now the third one is the non-selective scattering. This scattering phenomena occurs when the particles are much larger than the wavelength of the incoming radiation, thereby leading to approximately equal scattering of all the wavelengths, that is blue, green, and red light, which combinedly gives a white light. Water droplets and large dust particles are most responsible for causing this type of scattering. Due to this scattering, clouds appear white in color, and so as blurry, white, foggy appearance to the suspended water droplets during the winter seasons. Now, the second important physical processes affecting electromagnetic radiation is the absorption. There are gases, namely ozone, carbon dioxide, and water vapor, that are responsible for most of the absorption of electromagnetic radiations through partially preventing or strongly weakening the radiations as these passes through the atmospheric layers. Formation of ozone is the result of interaction of high energy ultraviolet radiations with the oxygen molecules present at an altitude of 20 to 30 kilometers in the stratosphere. Presence of ozone layer forms a protective layer in the atmosphere by absorbing the harmful ultraviolet radiations that may otherwise cause skin burns or severe skin diseases if exposed to the sunlight. Carbon dioxide occurs in low concentrations, approximately 0.035% by volume of dry atmosphere, mainly in the lower layers of the atmosphere. Carbon dioxide effectively absorbs radiation in the mid and far infrared regions of the electromagnetic spectrum. Lastly, water vapors present in the lower atmosphere are more effective in absorbing radiations as compared to the other atmospheric gases. Two important regions of electromagnetic spectrum ranging from 5.5 to 7 micrometer and above 27 micrometer are significantly absorbed up to 75% to 80%. Now, an important aspect involving interaction of electromagnetic radiations with the atmosphere is the atmospheric windows. The regions or bands of the electromagnetic spectrum which are not severely influenced by atmospheric absorption and thus are partially or completely transmitted through are useful to remote sensing are called atmospheric windows. In other words, gas molecules present in the atmosphere selectively transmit radiations of certain wavelengths, and those wavelengths that are relatively easily transmitted through the atmosphere is referred to as the atmospheric windows. The concept is illustrated in figure number 7. Figure number 7 illustrates atmospheric windows with wavelengths on the x-axis and percent transmission measured in hertz on the y-axis. Around 90 to 95% of the visible light passes through the atmosphere. The atmosphere is almost 100% translucent for certain wavelengths of mid and near infrared spectrum, which makes possible for remote sensing of satellite images in these regions possible with minimum distortion. The thermal infrared range from 10 to 12 micrometer is used in measuring surface temperatures of the groundwater, clouds, ozone blocks, ultraviolet radiation almost completely, and almost all radiation in the range of 9.5 to 10 micrometer is absorbed. Another important aspect involving electromagnetic radiation is its interaction with the Earth's surface. Electromagnetic radiations that are not completely absorbed or scattered in the atmosphere travels through the entire depth of the atmosphere before finally reaching the Earth's surface. The radiations strike the surface and again redirected towards the atmosphere for the second time before being sensed or recorded by the sensor. Generally, three types of interaction takes place when radiations strike or incident upon the surface, and these include reflection, absorption, and transmission. Therefore, the total energy of radiations incident upon the surface follows the law of conservation of energy, or the energy balance, which is written as the total incident energy is equal to the sum of reflected energy, absorbed energy, and the transmitted energy. Now, figure 8 illustrates the radiations striking the Earth's surface. Now, moving on to the final topic of the module, that is image resolutions. The fundamental parameters that describes the quality of image and the characteristics of image or spatial data include spatial resolution, temporal resolution, and radiometric resolution. In short, the resolutions can be categorized into 4 different types. that is spatial resolution, temporal resolution, radiometric resolution, and spectral resolution. Spatial resolution, it defines the degree of clarity of the ground features represented in a pixel. In other words, spatial resolution can be defined as the area of the Earth's surface covered in 1 pixel of an image. For instance, if a satellite image has 4-meter resolution, it means that 2-meter by 2-meter area on the Earth's surface is represented in a pixel. If very large ground area, say of the order of square kilometers, hundreds of square kilometers, the spatial resolution will be coarse and vice versa. Figure 10 illustrates spatial resolutions that an image can have. So in figure 10, different spatial resolutions of image are illustrated. Left one, nominal resolution of 1 meter resolution. Middle image shows 5 meter spatial resolution, and the right image shows 30 meter spatial resolution, which is considered to be a coarse resolution. Second type of resolution is the temporal resolution. Temporal resolution is the time taken by satellite to capture successive images of the same location over the Earth's surface. In other words, temporal resolution is the revisit time or repeat cycle of the satellite over the same region or location over the Earth's surface. Different satellites varies from multiple times in a single day, almost about a month's period. For example, temporal resolution of IRS or Indian Remote Sensing Satellite Series is 24 days. Spot Satellite Series is 26 days. Iconos has a temporal resolution of 2.9 days, etc. The third type of resolution is the radiometric resolution. Radiometric resolution refers to the finest difference in the radiation or energy levels in terms of digital numbers that a sensor can record in a single pixel, and thereby imparts quality to the image in terms of finer details. The finer the radiometric resolution of a sensor, the most minuscule details can be extracted in order to get more meaningful interpretation. Any digital image uses a binary format to store the data, which is represented by a grid where each cell bears a unique number in accordance to the brightness levels recorded by the sensor. And these numbers, again, these numbers are known as digital numbers. For an image, digital numbers range from 0 to a selected power of 2, which corresponds to a number of bits used for coding the numbers. For example, each bit records an exponent of power 2, that is, 1 bit equals to 2 to the power 1, which is equals to 2. The total number of brightness levels available depends on the number of bits of the energy recorded. If a sensor uses 8 bits to record the data, there would be 2 to the power 8, that is 256 digital values available, that is 256 shades between black and white, ranging from 0 to 255. However, if only 6 bits are used, then only 2 to the power 6, which is equal to 64 values ranging from 0 to 63 would be available in an image. Thus, radiometric resolution would be poor for 6 or 4-bit image as compared to 8 or 16-bit image. Figure number 11 depicts radiometric resolution of 11-bit image. In figure number 11, each pixel contains a value between 0 and 2047 according to the strength of electromagnetic radiations measured at the sensor, values termed as digital numbers DN. Now, the fourth and the final resolution, image resolution, is the spectral resolution. Spectral resolution refers to the specific wavelength intervals in the electromagnetic spectrum that a sensor can record. For example, one band of the Landsat thematic mapper or TM sensor records energy between 0.45 and 0.52 millimeters. in the visible portion of the spectrum. Wide intervals in the electromagnetic spectrum are referred to as the coarse spectral resolution, and narrow intervals are referred to as fine spectral resolution. For example, the spot panchromatic sensor is considered to have a coarse spectral resolution because it records electromagnetic radiations between 0.51 and 0.73 millimeters. On the other hand, band 3 of Landsat thematic mapper sensor has fine spectral resolution because it records electromagnetic radiation between 0.63 to 0.69 millimeters. Figure number 12 illustrates all four types of resolutions for the Landsat thematic mapper sensor. The source of figure number 12 is EOSat. Thank you for your kind attention.